Going live. Now I should be live. Stream is here. Let me check myself if the audio is working. Start recording. Yep, recording works. There's still a tiny bit of ringing if you hear it really loud. I don't know where this comes from. Still a bit better, but yeah, whenever I get to I know maybe the receiver does some ringing yeah, maybe the recorder makes a bit of streaming of ringing when I speak too loud and it puts too much on the line. So I just don't speak too loud. I have a compressor now which amplifies my voice if it's not loud enough. But recording works. Concurrent viewer is myself. I view myself. That's working. So time to continue with the IOVoodoo. 3 days ago I've explained the project. I won't do it again. The summary is right there. You also see it on this part. Use analog multiplexer. Okay, this is done. And what we presented last week was the firmware. I've started working on the schematic, and the schematic is now kind of done. At least the first version is, because with the schematic it's not completely fixed and then you do the layout. It's always a back and forth, and you have to change the schematic if something doesn't work and then put it back in the layout. But this is how the schematic looks like. This is the software for my EDA software I'm using is Lepton EDA. So we have the USB input, USB-C, which is directly connected to the microcontroller, which is on this side here. With too much on the left. We also have on the left side a programming port to program the microcontroller. USB and programmer are protected using this TPS diode array. Microcontroller is also connected to SPI, external SPI flash memory. This way I can stock information about the identified devices without cluttering the internal flash of the microcontroller. We have all the bypass capacitors for all the I/O lines. The advantage of the PSOC is had multiple voltage domains, so you can see the different I/O lines could have different voltages and do have different voltages. We have some with 5 volts. Everything which is ADC related is at 5 volts. And I think the USB is also at 5 volt. Yep, the USB is also at 5 volt. This is VDD. Then we have 3.3 volt for the SPI flash, because this is rated for 3.3 volt, although I think it works at 5 volts correctly. It break it too much. And just for the SPI, well, not only, but mainly for the SPI flash, I have a 3.3 volt regulator. This 3.3 volt is not powering any other devices, just this one. And it makes it available on this target voltage select. So on the right side, we have the channels. This is the external connector where you connect the target port to, where you want to identify the signals. All the channels are protected using TBS diode. I don't want any risk of breaking the target port, because sometimes they're very expensive, and this is kind of a reverse engineering thing for also expensive devices. We also have resistors which are inline, so they limit the current kind of, but not a lot. They're mostly there to limit the ringing when we speak high-speed protocols, as the purpose is not only identify the pins, but also to be able to speak UART, SPI, JTAG at a very high speed, well, very high speed, above 1 megahertz. And here we have, on this side, we have the voltage selection. So the user has to manually select the target voltage. Either he provides the target, I should write it somewhere here, target voltage, yeah, it is kind of, no, let me write the text, add a text. So this is target voltage inputs. It's just a V target input, target voltage base, yeah, target voltage inputs. So either either the user provides the target voltage from the target board, or he can select 5 voltage or 3 volt and 1.8 volts, and he can also provide the target board using pins. 1.8 volt is not exposed, but he could cheat by shorting 1.8 volt with a jumper and then also shorting the target. So you would have 1.8 volt going through V target, because that's the target voltage, and then going to the input, which will become an output. That would be how to cheat 1.8 volts by using 2 jumpers. I will only provide 1 jumper though. And that's it actually. We still have some, this is LED to have some activity indication. Whenever I do something, we have a switch mainly for entering the bootloader mode, so we can reflash it. And then there are lots of option components. There is something which not here. But this is not connected correctly. Now it is. And with that, the schematic seems to be complete. As I said, no, it's not. I see another mistake, and these are things you also see when I will also see when I do the layout, board layout. Here, there was a ground missing on this capacitor. It is optional, and it is there to remove the need of fairy beat and the high voltage noise on the 5 volt lines. And now that this is done, let's increase the font. Now we can export the schematic, break print, I think. And by print to hardware, we can see the output schematic generated automatically. This is not needed anymore. Yeah. And the output schematic is generated. You see that the script puts in the version, which is done by hand, and then the revision, which is the number of git changes there were on this file, and this is the git hash, and this way I know exactly which this corresponds to. Actually, what to up is because this is not version 1. That takes a bit of time. It is also generating the board layout, the print for the board layout. The resolution is a bit high, but meh. Let's wait until this is finished. This takes a bit of time. And what I also did, meanwhile, so since last time what has changed, the ground symbol, it's not the earth symbol anymore. So this is more the earth symbol than the ground symbol, and I wanted the digital ground symbol. This one. Also, everything which is voltages is now arrow pointing up instead of 3.3 volts. No, instead of this one with the bar. I think it makes it a bit more readable because the bar, you never know. I changed that, and what I did is on every component I've added the footprint, and these are links to the footprints are generated. We've seen 3 weeks ago that I generate all my parts, that I specify all my parts, and it generates the symbol and the footprint. This is actually the symbol generated from that using Kida. Now, before we continue, I have to put everything in Git. Yeah, let's put everything at once. These are the connectors. No, these are the footprints. Let's only put the symbols for now. So these are the old ones which have been modified. I don't know why the symbol has been modified. It says it's been modified, so it's modified. I know why. I changed the script for drawing lines. Exactly. I know why this is modified. But now let's just add this. I know why I git commit, and yeah, my hardware project are also controlled using version control. and it allows me to do the changes. Thick line, thickness drawing. Git status. I also added a read and some note. Plenty of things actually. This I can test points up. RAM I don't use more. It's add custom power tools. Now we add all the other components. So these are made by hand as power symbols. But next components, all of these are the connectors. Didn't have them previously. So let's all of them up it add connectors. Now the readme is not complete. I think the reg file is only 1.6. And you see here there was 2 times color when exporting the schematic. It's commit reg file. It minus have issues with uploading. Dropped. I have to disable my Wi-Fi. Seconds. IF down. Set up, set down. You don't see what I'm doing, but right now I'm just disabling my Wi-Fi, so I only use my network card, and it's a bit more stable for the stream. I don't know if they were, it did sometime hang, but yeah, it should be more stable. Now we add the schematic. And schematic big symbols, add prints. That's mainly that. Up. Yeah, it's not very atomic. I could have made several commits, but that's good enough. And now, actually, it should, if I make print, should regenerate break print. It doesn't, because the file didn't change, but we have had 1 commit more. IOVoodoo schematic.pdf, and now if I print, we should see version 2. Schematic. Don't. That's weird. And there is a second change on this one. We should have revision 2 on this one. Don't. The versions. That's why. So it copies the schematic, puts the version number, and then it exports it. And now it should be version 2. The script is working correctly. Yes, now it's version 2 with the git tag. I think it's ending or the beginning of the git hash. I don't remember. And you see that this comment is blocked. This case is. But let's start with the. I will always keep the schematic on hand. So let's put the schematic where we can always see it, like here. It helps during the layout to have the schematic always there. And now we will start drawing the board layout. And for the board layout, I'm using an EDA tool called PCB R&D. It started as a fork from Gila PCB because this didn't have a lot of updates. Now it's completely different now. It looks very similar. Under the hood, it's completely different, and it's a lot more powerful. PCB R&D. That's how it looks like. Yeah, very archaic, very like for 20 years ago, something like that. But I love it. Although there are plenty of changes which have been made since I did a last board layout, so I don't know if I will remember everything. But we'll try. And now what we want to kind of export the schematic to here. So we have the components. What we could do is import directly the schematic, but instead what I do is I make something which is very common. It's a netlist. The netlist tells which component is connected to what, and that's enough. So you don't have to pass the schematic. It's a kind of like, yeah. Let's talk about EDA tools. Very often you find that the EDA tools have everything integrated. The schematic, capture, and the board layout, and maybe some Gerber viewers and things like that. It's not always like that, and whenever you use them, sometimes you feel that they're different things. Well, they are different things. You don't generally use the same software like for everything, for 3D drawing, 3D animation, and then doing some 2D graphics. You don't use the same software. Same here. The schematic capture can be done with a completely different software than the board layout. And that's my flow here. I have a completely different program for the flow, for the board capture, for the board layout than from the schematic capture. And what is very important is that both of them can kind of communicate, or at least you can put the components from the schematic to the board layout. And this is done with something with an interchangeable format, standard format, like you would, for example, whenever you finish the board layout, you send some Gerbers to the one who produces the board. This is also kind of a standard format between your board layout program and their machine program. But same here, the netlist is also a format, and this allows you to use most of other board layout programs. I think this is supported by other board program, or should be. And now we can import. It's called, they call it schematic. It's not schematic, it's a netlist. And yeah, now we have all the parts on the side, and we have no errors. That's good. So every part has a footprint, and the footprint seem to be okay. And if we can look at a footprint, for example, this is the USB connector, and if we look at the rat's nest, yes, we also have rat's nest is which pin needs to be connected to which other pin, and we see that from this component, these pins need to be connected here. So we know that the netlist, it is documented, the connections are documented. These connections, these wires, all these wires are documented. That works. What we need to do, so the boards, it's maximum 10 by 10, because these are the limits of most prototyping services, but we will be a lot smaller than 10 by 10, so I don't really care about the size right now. Although I could, let's change it. I think it's edit properties here, preferences. Yes, board size. Here we change preferred unit because most of the thing will be surface mount components, and most of them are in millimeters. 100 millimeters, 100 millimeters. That's the maximum. This is not important. PRC is a lot later. What we also need to do, so this is the maximum board size, and it's plenty enough. You see, we have only one microcontroller. It is large, but the largest component is the connector. The 20-pin IDC connector, right angle, so we can connect here. We have, although I thought my board would be a bit smaller, but with all the components, it could take 5 by 10. We'll see how compact. We don't want it to make both sides to make double loaded. We could, because it's done by hand. So double loaded mean that on a PCB, like something like, okay, the camera doesn't work anymore. Why doesn't the camera work anymore? Switch it on. And yeah, camera is not active. Let me restart OBS so the camera can become active. Yeah, let me restart OBS. I'll be there in a couple of seconds. So I should be back, and it should say that I have data. Yes, I do have data, the audio works, and the camera is here. Perfect. So double loaded, double-sided means that you have components on one side and on the other side. It's not always done like this. So you do this when you are very restrained on the board size, and you cannot put all the components on one side. Generally, you don't like to do it because that means that you need to pass this device 2 times on the reflow oven. One time, because the reflow oven only reflows what's on the top side. So you pass it 1 time on the bottom side because there is a small components and they hold, and then second time you again pass it on the reflow oven on the top side. And because these are small components, the solder on them, although it will melt again, not completely but mostly, it will hold the component in place. If the components are too large and the solder wouldn't hold the component in place, you have to add some glue, and this costs money. So passing the board 2 times in the reflow oven costs money, adding glues onto the component costs money, so double-sided devices cost more money. So this is why whenever you can, you do something which is single-sided load, where all the components are on one side. Here, nothing is on the other side. No component is on the other side. And we also want to have some single-sided load because we have enough space. This is a prototype. We are really not constrained by space. But we wouldn't really care if it's one-sided or two-sided because we're soldering by hand. So the manufacturing cost of putting it 2 times in the oven isn't there because we do it by hand. First prototype. Afterwards, it's more important for the second prototype. Once this works for the second prototype, we have to pay attention to that. So we have all the components. Now we need to change the routes. This is here. Signal, so most prototyping services allow now 5 mil. It's tiny, but they allow 5 mil signal routing. But what's very important is how do you do that, or how do you do that? Let's take, for example, PCB way. PCB way. You have to check what their capabilities are. And on PCB way, 2-layer here. Where is it specified? Code now, prototype, thickness. I don't. Here, board specification. Yeah, basic setup, trace space, 4 millimeter, 4 millimeter. If I go to another popular prototype manufacturer, like GLC PCB. Here capabilities. You have lots of them, minimum clearances, minimum tray space and spacing. Here, 5 mil, 5 mil. So trays with 5 mil and spacing 5 mil. So we can abuse that. It's tiny, but we can abuse that. So what I often do is signal is 5 mil by 5 mil and power is 10 mil with the clearance of 5 mil. That's good enough. That allows me to everything. Great. What is important also is changing the pad stack, the via. And for the via, I have to check again what was that. What the whole drill hole size. I think it's 0.3 millimeter for the drill. Oh, they changed it. It used to be 0.3 millimeter. Now the minimum drill size is 0.2 millimeter. It's really small. Minimum hole size 0.2 millimeter. Ah, here. Ah, yeah, no, I was right. For single and double layer, the minimum hole size is 0.3 millimeter. It is still really, really small. And for them, code now, if we code now, where is, spacing. Now we can pay more or less. Does it cost more? That would be interesting to know if it costs more to have 5x5 or 6x6 is less expensive. Do I have a board available so we can check it? Always the size. Let's check. 100 by 100 calculate, and I have to enable JavaScript. 100 by 100. This quantity 5 is plenty enough. We will make 1 or 2. So for this, once we start higher production, there will be more. But for now, 1 or 2. Calculate. PCB cost $5. That's what I expected. And 5.5. Oh, okay. So let's put it 6.6, because if we want to use PCB way, 4.4 is the minimum, but 6.6 is recommended. If you use GLC PCB for $2 and 5 boards, you get 5.5, 5/5. But let's put 6.6 so we are free to choose whichever manufacturer we want. If you are, and because it's a prototype, what you can do is from beginning on, that's on a prototype manufacturer, follow the recommendation. I'll try to keep my options open. 6, close, and then for power, let's make 2010. 2010. And now regarding the drill size, let's go back to here. Here we know that it's 0.3 millimeter. Min diameter, yeah, 0.4 millimeter. Generally, I put double the hole size. It really depends. But what's the minimum? Min hole size 0.3. Yeah, same here. So we will put, and the minimum. What was the minimal ring? Minimum via diameter 0.4. Well, yeah, we'll put 0.5. So for edit, pad stack. This is the pad stack. Let's edit it. I want everything in millimeters. Can I change it here? Hope now everything. Edit. Yes, everything. By default. The pad stack. So the advantage of here, normally the ring, when you use vias, don't care, don't know. You have round drills, round holes, but you could have octagonals and things like that. Most of the CAD software, I think, doesn't support very exotic things. Maybe they support hexagonal or rectangle, but they don't support any other kind of form. PCB R&D, everything, the footprints, for example, are pad stacks. They're called pad stacks. No, not the footprints. Now, the holes in the footprints. So you could have any kind of shape, for example. No. Oh, really? It is called a, no, it's still called a subcircuit. Let me explain quickly. So let's cancel this. The footprints are called subcircuits because they're really mostly a drawing, but in a small format. So you can think of it with a board layout, but just for one part. This is why it's called a subcircuit. Within the subcircuit, you have elements, mostly the pins where you connect to. These are called in DBRND pad stacks, and you can define that this is a pad or this, like here, so it's only on one surface, or it is a hole, so you define the oval shape and then the oval pad, or you can define it round. You can have a lot of different things. You can also have a hole but just on one side, for example copper, and not on the other side. That's also possible. And the pad stacks are quite amazing how the power you have, which was one of the really strong disadvantage of KIDA PCB. You were really limited by the pad stacks. Now you can have almost any form with that. And this is why also the vias are just pad stacks. You just define which one you want. And you can edit it, you can create it. And so here, the top copper, we will change it. And we don't want automatically generate shape for delete. How do I change? Circle, JMac, circle, generate here. Circle size 0.5 millimeter. Warning. Millimeter. Now it knows. And this way you can also any unit. Millimeter. All coppers, yes. Exposed top bottom copper. Paste. No, we don't want paste, and so exposed mean, do we want to have solder mask on them, or do we want them to be tinted? I like having solder mask removed from them because I can then solder on them or put a cable on them. Whenever I do prototype, if I don't do a prototype, I will remove this exposed copper top and bottom. And then we don't want paste on the thing. Generates, and yes, this is what we have here. Top copper, okay, full geometry, and now we have this, and we see also what it generated, and here we see that it is open. The solder mask is open, so we can have access to the via, and that helps me probing. For example, with an oscilloscope, I can just touch on a via if I cannot touch on a pad. For example, when you have BGA, you have signals going under the BGA somewhere, often through a via somewhere else. You can probe, because you cannot probe the BGA ball, which is under the chip. You can probe at least the via. If it's tinted, so covered with solder mask, you don't have access to it. And so this is use selected, is for signal. And now for the power, we will do the same thing, and we will increase everything by 2 almost. So we will have a pad stack, edit the pad stack, generates the size of the hole will be 0.5 millimeter, and the drill 1.2. So millimeter up, generates. So often I have power to double the size of the signal, but something is wrong here because there's no hole. Edit 0.5 millimeter and drill. Wrong size. The size is 1 millimeter. That's the circle, that's the ring. Then the hole is 0.5 millimeter. The signal sizes and power sizes depends on how much current you want to have. There exist calculators for that. I use of some box. And now it looks nice, but I forgot to remove the solder mask. 0.5 millimeter. Exposed copper generates. those, and this is how it looks like. And I think we can see actually how much the solder mask is pulled back. I think it's 0.1 millimeter, but that's a rule. Top mask, it's even less than 0.1, else we would have 1.2. It's 0.75 millimeters. This is, there's the setting somewhere. You selected, close, and now save, and we are almost ready. So whenever you do board layout, you start with the placement, and then you do the routing. That's kind of important. We put it in the middle so we can have space. That's on the right side. That's a connector for connecting the outside, so the board will finish right here, so we can solder the connector on here. Although we could solder the connector, we could have the board going up to here, so we have even more, a bit more trench under the connector. Trench under the connector. This is huge. It could be smaller, and actually it will be smaller. I use this connector because if I don't have any through-hole pin, I have a lot of space, and if I don't have enough through-hole pins, I could use something which is boxed, a shrouded header pin. But this shrouded header pin is far too large. I will probably change it and have just a connector to it. For now, let's put it this way. And this will be the voltage selector. We want to have it very near this thing, because this is where, can we have the whole board as large as this connector? That would be nice. Up, rotate, it's F9. Yes, I still remember a couple of things. Then I want to get the rat's nest. Yes, rat's nest. Size, selected, erase. Don't want to watch them for now. So the USB connector will be this side. If possible, I can make it 5 centimeters by 10 centimeters. This way I can have 2 per 10 by 10 board, but I don't really. This is the programming. The programming board will be next to the microcontroller. Although I will put shrink tube on it, so we will not put it next to the microcontroller. We will put it next to this connector. The connector should be centered. We're not in middle, so it's not. So this is where it's useful to change all the time the grid. Now we have when mils, the grid. What is the grid? Grid is in mils, or is it grid is in mils? We can now center this to this point instead of this point. And here we have the center of the object on a line. This device on the line. We can in this unit. This is too large. This way, it will be above the connector, and that's for now. I want to try everything on this board size. Maybe it won't work. So check later. So I will add it next, and I want to put. Let me check. Let me show you what I mean. Why I want this? I want something like this. This device. This is the Sega J-Link. Okay, it's a clone of the Sega J-Link, and you see here we have the connector. They didn't put the board, so you could put the board under here, and this will give you a bit more strength when you put on the button. But really, the 20 pins soldered on the board, if the board is good enough, it's plenty of strength, so you don't really need to I will still add the board under it because we can. We have enough space. If you want to save some space, you shouldn't. So you pay more for the board. Here we will pay, because it's a prototype, there will be no difference in price. As long as we don't exceed 10 centimeters, there will be no difference in price. Same here. Here they added it to the edge. They could add it a tiny bit back, so it's a bit more robust, and my connector will be more robust. But the idea is that I will put, and here it's a bit larger than the connector. I will have the same size as the connector, and then I will put, like here, a shrink tube on over the whole device once it's finished, so it doesn't short anything by accident. They added the thing here, so I need to cut a hole. If I have the programming header here, not too much of a problem. And I can easily come with probes. Yeah, so why not have kind of this form factor? Up. So I'll put it here. I can set points to it if I need to. So this is centered. This is right next to it with pin 1. Oh, and the advantage of, so here pin 1 is not, the advantage of having all these footprints generated, they all look the same. All the sail screen have the same width. They all have this kind of same marking. Here, for example, pin 1 is indicated by a dot on all of them, except with this one, we don't need to know which one is pin 1. It's quite clear that, well, there's no real pin 1. But whenever we need also the marking for the LED, I think this is, I never remember which one is the anode, which one is the. But here, for example, on these SOT devices, these are the diode. Yes, diode. Here you have pin 1 marking with the line also on the corner. This is the package size, and then this is extended corner, show pin 1. Actually, why it doesn't show? Oh, that's a shame. I have to check why this is. No, top assembly, maybe because it's not enabled. Yes. We have even more information on the top assembly. You see this line, this is what's called the courtyard. And it shows you where you shouldn't place any components within this courtyard, because the pick and place machine might bump into you or might collide because it's not very precise. The pick and place machine is not very precise. So it might move. So you should put any device within this courtyard. So next to the component, and see it on the top assembly. So this needs to get up. So this will be the voltage selector with a jumper, and I will actually put a bit more on the left because I want to add marking. Yeah, I want to add marking on the side to it. What is what? That should be enough space. So we have the programming header. Will this be big enough? See? Yeah, probably. Probably. And yep, the reference designator here, you generally want it outside because afterwards you want to read which component. So whenever you populate it is mostly important when you populate the device, so you know which device goes where. But once you populated it, for example, if you have this chip on here, you wouldn't be able to see U1. So for debugging, it's not really useful. This is why you often pull it outside of the box. And we do this for let's put it here. I would love to put it here, and actually if I put header, it's good enough. But if I put a shrouded header, you don't see it anymore. So let's put it here. A lot of space. That should be route the signal. I don't know how to route them. Check that. data. Let's put the, I always try to put, yeah, we can put voltage. Where is the voltage output? I think these pins are the voltage outputs. Is it written? That's terminal 3. Okay, that's not the voltage output, isn't it? That's ground. Ah, I didn't name it. I think these are the voltage outputs. We know that this is ground because the netlist tells that this netlist is ground. Here we don't have the name. I could have added, for example, VBus. In the schematic, I could have named them here VBus, and now we would know that this bus line. Let's add this to the microcontroller. Yeah, why not next to the microcontroller? I don't know on which side it is though. Data. It's just a general placement. There will be plenty of changes. Use will be somewhere here, and we will keep them on top with the voltage regulators. Where are the voltage regulators? Yeah, here are the two voltage regulators. 1, 2, 3 pins. The 2 voltage regulators. Then we have plenty of capacity. Up the button. Where do we want the button? Let's put it below plug. This is pin 1. This, okay, it's good because I think these 2 pins on the buttons, this is really a pain. These buttons are double row, double terminal DT, DP, DP, double pole, double throw. But so you have 2 switches in that actually, but I never know. I think these 2 pins are connected, these are not connected. I'll check that. I always forget. Plus, it's a bad thing. Check button. Tack. Oh, here 6mm button. That's the one. Let's use a multimeter. Ooh, okay, multimeter. Deep. And I think these 2 are connected together. Yep, that's what I thought. These 2 are connected together. So on the side where the pins are not visible, these 2 are not connected together unless I press on the button. Press on the button. Yep. Yep, that's how it works. So the footprint is correct because if we look at the schematic, pin 1 is 1 input and then connected to 2, and which is the 1 pin. So this is correct. 2 are not connected. Once we press, they're connected. These 2 are connected though. So what we can do is rotate it somewhere. We have all these diodes. So the first one is for the USB and programming. So it 1, it from the schematic. Actually, I have the 1 on the schematic. It's for the programming ports and the USB. So it will be somewhere around here. All the other diodes are for here. Next. Up. Up. So now it's a very general placement. So just to have an idea how to put the devices. And next to the fuse, we also have actually a capacitor. So this will go somewhere around here. We have the E10, and then the C. There's also a search. The LED. Let's put the LED next to the button because this is what the user mostly interacts with. The button for the input, the LED for the output. Yeah, put it here. We could put it next to here to indicate there's activity on this port though. A good question. Do I want it fraction or do I want it next to the input output? Because it shows it's the input output. Yeah, let's put it next to the input output, and this way what we do is that whenever you press on the button, you don't cover with the finger, you don't cover the LED. Test points. And here, one for each channel with channels, and we will move the silk. Or I just further part points. The test point goes to the 2 seal screen. First one to point 1, and the test point, I don't know, we don't know the orientation of this device yet. The test point comes, but I know it is next to the microcontroller. They're all resistors, they're all plenty of capacity. Coupling, the decoupling capacity next to the pin. Although it is not shown in the schematic, I put all the capacitors here, but I know from the layout that these bypass capacitors need to go next to the corresponding lines, PA and so. I think I have more capacitors than resistors now. 25 resistors, 8 resistors. But it needs C10. That's the one we were. Now we found C. Ah, these are even. C10 goes next to the fuse, next to power input. The power input be the USB. And no, we won't use any for delivery. So most of these anti-pingers, in theory, you put them as to the microcontroller. We will put them not too far away, but not really. Resistors, let's add. Should have the still screen of the thing. And for example, like this friends, because you see difference the capacitors, LED, that although they are all the same package. You see resistors only on both sides. Now capacitors also, but they were all around. Okay, so they're not that different. But although they are the same form factor, you see the pads of the resistors here are smaller. The capacitors, they're larger. But I really thought that there would be a difference. But for example, on the LED, there is a difference. There is also an on one side. Oh yeah, the difference between capacitor and resistor is just pad size. So, what do we do next? We try to have the right orientation for this device, so the signal goes as easily as possible to this device, or actually devices, the resistors, and this device. Yeah, let's orient it to the USB, because the USB traces need to be very parallel and as short as possible. We don't want it to route it to the other side. So connect rat's nests to selected. Because it goes through. So here on the USB, it goes R9, and R10. 9. This is here, and then I'm blind. They put all the no. I flash. Crystal oscillate. And yeah, the oscillator. The oscillator, you see, the oscillator is huge. For the final production, I will have a oscillator which is 1/5 of this size. But for now, I have them in stock and they're good. And it's expensive. I have plenty of them. I need to get rid of them. So yes, R9 and R10. R9 here goes between USB and the microcontroller, and put it some components. I have to put optimized route. This is all of them. Just for the selected. We see that these are the 2 pins. So we will rotate this one, this side. This will allow bring the delay. And here we can no, it's okay this way. Bit of a pain because we need somehow to pass through. So a good design would be that the pins go through here, and then we can. We actually can. It's not ideal, but it is possible if we do it this way. And have the signals go here and then go to these pins. Then have vias, the other thing. So we can do it this way. And the rat's nest don't get updated, but yeah. Now I want to have the grid because everything is surface mounts. Now I want to have the grid because most of the things are now aligned. This doesn't need to be aligned to any of these. Only these two should be aligned to look nice. This is in the middle. This should also be in the middle. So it looks nice, but everything else don't care. So we will change the grid to millimeters. Millimeter grid size 0.1 millimeter. Oh, it's too small. 0.25 millimeter. and we align everything to the center. How does it work? I don't remember the button. View grid, realign grid realign. Okay, and we see that all the grid is realigned to this component. At least what's important is that the center has a line. And yeah, really there would be the traces, because they're different, because USB has differential traces, we want them to be as symmetrical as possible. Where does this connect to? Actually, I didn't put any. It's okay. We could put some inline resistors between the programming pin and here. Does their board do that? Doc schematic. So this is the development board. No, they don't. No, this is the wrong program. Oh, where is this side? This is a kit prog. There has a connection. Kit prog. Yeah, this is the header, and this goes to ProgReset directly. ProgReset, yeah, they don't put any inline resistor with SVT-IO. Connected directly. You could put some inline resistors to really to add some security. I think I won't add it here because it's a programmer, and actually what's more important is that these are pulled high. Are they pulled high by anything? You don't have to. I don't know if it's a recommended design from JTAG that the lines are pulled high. So here it's not pulled high, it's not pulled high. Here it is not. It is not pulled high. On its own, it is not pulled high. Let me check on the USB specification, or USB JTAG specification, if they recommend pulling it high. You find the documentation stream. I know. Yes, stream. Resistor. About JTAG ports. Pull up, pull down, or omit it for clarity. They add a series resistor, but for TDO, we don't have any TDO. Again, signal integrity. Router do the same for, so TDO, we don't have TDO, we have TCK. TDO, TCK, here they add nothing. Here they add something for TCK, but this is if you have multiple, actually, if you have multiple targets on the chain. You can see that TDO comes here, TDO becomes TDI here, and then output. And if you have too many of them and they pull too much, you add a buffer, just an op-amp or a buffer, so this TCK cannot draw away from this TCK. Here the solution prevents to move point and tank ensures single integrity with minimal overshoot. And because you add buffer, which has a very high strength, you add an inline resistor because this can output like 20 milliamps, and you don't want this to ever happen, so you put an inline resistor. This is for Which one? This solution is matching between this Q. Okay. So here, the problem with this solution, so it's a huge tangent, but here the problem from this solution is that when you put a buffer, you add kind of a delay because it goes through the buffer realigns it, and then output. The delay is really small, but if you want super high speed, it can make a difference. This is why you add buffers to all of them, and this puts the delay or the skew to the same to all signals, mostly the same, because there's still a tiny bit of difference and a kind of tolerance within this buffer, but at least that's the idea. And if whenever you put a buffer which is really drives strongly, you add an inline resistor. So this is this for the streams, but we have only SVD-IO. We don't use JTAG. We just use series terminal. But they didn't add any pull-up. 50 ohm target impedance. Ohm. Here. We see. We have added dependence drive strength, so we could add a 22 ohm resistor because we don't know the programmer which will be connected to it. It could be anything which is low, high. But since we have plenty of 22 ohm, we could add a 22 ohm inline resistor. Do we want to do that? Termination therefore. That's 2 more resistors. Here. If it is determined that 0 are not required, it is recommended that 0 links must be placed close to the driver as a fallback option. Yep, that's true. So ideally, we would have added termination resistors, and I think I will put them. For reset, no, but it's not a high-speed signal. For these two things, yes. So we will add resistors. And since this is driving, so we have that on the side. Up. Resistors. Do we want to? I think it doesn't matter if you add this before or after the 22. Let's add the protections after. There still can be 0 ohm. For now, we will add these ones. We can still try out. And if we don't require them for the end, then we can remove them. This allows us to save a couple of cents, but a bit of space. For now, I don't have any space constraints, so let's do that. Reference designator is not 26. We don't know which one it is for now. Again, it's not 26. It's unknown. Those. And connected. Maybe there are already inline resistor on the driver's side. Actually, they should be on the driver's side. We shouldn't have to add them on our side because we are the targets, and they say that it should be near the driver's side. We are the target side, so we don't need to add them actually. We are not the driver's side. We don't have to add them. So let's undo everything. Let's leave it this way. It's the programmer should be that we are far too away from the one. So that's good this way. This is clarified. Now, refresh the rat's nest. PR is for all of them, yeah. You see, this is all we have to route. Please. I think CS would be nice to show only the rat's nest for the selected one. I have to define the shortcut for that, so that for that yet, yeah, adds to selected address and selected. That would be. Ooh, they select. Ah, no, it's because ground, and these are all the ground pins. No, this is not a ground pin. Ah, 5 volts. Yeah, this is 5 volts. But what's important is that these signals have to go here, and then where do they have to go once they go here? Down. Why isn't it? 10 resistors. JTAG. So. Oh no. Why aren't they? Ah, here. Ground. That's clock goes. Should go here too. There is something going wrong. When should they go? SVDIO 20 and 21. Pin 1 is here. So 20 should. Ah, they go. Yeah, we just don't see it. They go here, then they go forward. That's okay. The TVS doesn't need to be before, does it? I think it doesn't. Does it matter that the TVS is between? That's a good question. I have no idea. Is it okay to have the TVS here and the signal going first from the programmer to the pin and then to the TVS? This will still clamp. Let me check in the TVS reference. So this is JTAG. We don't need this. Programmer specification. Up. Data sheet. Application. Somewhere. Search protection. Search protection example. Calculation for search protection behavior. How to ensure. Okay. And the tracks. Ah, here. The same way with the tracks. Data lines to must be as short as possible. Yes. Ah, and this is what I meant. This is what I meant. You don't want to be, well, you don't want them to go off this way. You want to go inline. But we can't, not for your USB. Although we could. SD search out, yeah. Probably it has to be inline. Needs to be inline. Yes, it needs to be inline. So this we don't need anymore. Oh, it is recommended. It is optimal if it is. And since the pins are here, what we can do is put the programmer the programmer around here. Not this programmer. This is wrong. Yeah. Signals. This one. Put it. Still not sign. Well, we can. Let's make it this way. Let's have this line to this. Both. Not. I don't want it. Although that really depends. I don't want it too near because I still want to have access to the pins. If for soldering, I have to solder first the first mount and then the screw hole, but this is generally the order because if I had this connector first, then I have no way to contact these USB pins from with the soldering iron. I cannot touch this pin. The connector will be in the way. This is something you don't see, but if you look at it 3D, you take. And it's good this way. So have it routed sides. Let's see how we do the routing. Most important routing is this high-speed differential. This is more important. That's T1 here. The lines. Okay. We need also to put, so this goes to which pin? The test point goes 650. Should test point 1 is somewhere around here. Then the LED away. This needs ordered 2, 3 because it's 2, 4, 4, 5. Then we can also put the count it afterwards. So the resistors are R11 to R26. That's 50. R11 and show that's shortcut. I don't think you can, but in configuration it's up. We start with R8, then we go R11. Does it make sense? This is where we can see we can switch the ports. We can switch between port 0 and port 2 if it makes more sense for the routing. So let's add with R18. R18 once. Then we can see if it makes sense to switch the signals in the schematic. Up, up. Back. I really need something. Repeat this. Let me check. There's something weird. Y D5 2 3 2 3 4 5. Oh, R18 is the last one. That's with R9. That's it's. I could rename the resistors. Where's R19? I don't see it. R19. This is what. R19 or R19 and R. I have to check. Starting to annoy me. Preferences. Keys. Add. Click here to press any key. ES. Select state to. I select. Add address. Ah, it's a command. Ah, I get it. How does this work? Oh, this is my victory. Editor. Probably here autoplace. Ah, we can search. Key, translate key. Okay, let's just shortcuts. Show. How is it called? Too many configs in the editor. Binding. Binding. I don't know the action for address now. Cannot edit it? Come on. What does this do? Click here, then press X. It will be filled automatically. But I want more than one key. Is this already used? The problem is I don't know these already. Maybe Alt R, like routes, or Alt S. Let's try Alt R. Translate to enter key. Okay, that's wrong. That's here. The tooltips text has been copied. It's not ideal. Translate to enter the key description here. Oh, now I get it. Okay. It translates to, so if you press one button, it translates to the sequence of other things. That's nice. It's not exactly what I had in mind, but it's also nice. Editor. Grids. It must be somewhere here. Translate key. But that's our thing. Where is it? We don't need this anymore. Key binding here. Key binding. Plenty of key bindings. Draw polygon. Okay. Ah. Ah. Plugins I don't. Not bore you in this. That I'll find it up. So connects. Selected. Oh, it looks nice. Oh, by chance, it's the right pipe. It's the right way. Really by chance though. Maybe these pins are not correctly. Let's check between this one. Connect, threads nest. Ah, here it is. Here. Select shortest. Address set. Ah, this is not optimized. And actually, I could have already seen it here. 71, 72, 73. And actually, this is optimized. This is not optimized. So I could switch this around. Why is it? Ah, because it's increasing. So I have to switch the order here. And here do I have to switch the order? Channel 0. Yep, I have to switch the order here. So I have to switch the order on both of them. And this will ease our routing because we have the freedom to select on which channel goes any of the pins. It's not really important for us. The code can cope with that, and that makes it nicer to route and nicer to see. So we will do that. We will do it now. Damn it. Edit preference. Saved. So let's change the schematic, the routing. Oh, yes. So this is bottom one. Yeah. Actually, let's have routing. Thing. Yep. We save, we export the netlist. Now we re-import the netlist. Oh, know how to do it. Import the netlist, import up. There's also a command for doing that, but now select again the parts. Connect, but we see it doesn't work. What's gone wrong with the netlist? No, it does work. It does work. It's just that the resistor has been the wrong size. Here. Here. Yeah. It has worked. So now we can add all the resistors. This edge. $11. 12. Oh, that's okay, you see the courtyard overlapping. Now it is not overlapping it. Oh, the crystal. What about then we do the crystal, then we do resistance. What I don't. But only put 8 next to each other. 4, 5, 6, 7. So we'll have 2 rows of 8. Or actually 4, 4, 4, 4. Cross over. We will have it like the pins actually. Yeah, we will have it. We will have them like the pins. 30. Then we can also change the did I miss one? Ah, no, it's not correct. Hold on. Could add, probably we don't have it. Add one width, not easy. Some are next. Yeah. So 19. One. I could, instead of, it would be at least, that would be a lot smaller. By resistor arrays could be better if, I don't know. I don't have any resistor arrays, but they would be a lot smaller. I think for the final design, for now, I will use single ones. I think for the production design, I will use resistor arrays because so many of them, and that will save a lot of space. For now, we will keep these. Also, a tiny bit easier to solder the resistor. These individual ones are easier to solder the resistor. Not that much more complicated, but still a tiny bit. Ooh, we'll have enough space. 1, 5, 6, 7, and one more. Yes, I want this to will not be this. I will change the footprint. I will not put this routed header. Change the footprint afterwards. So we will have just a pin header, something like this times. Actually, I can change the library for this. Have a 2 times header. Link this afterwards. And then we will save some. This is just if you want a connector. We don't want connector, we want jumpers. So this is not the ideal one. But so 4, 5 and 26, these are the last one. The last one. 5. Okay. Let's have the rough placement of these devices. Now, normally if we select all and add the, should see nice rat's nest. Ooh. Okay, this here. Here goes here. This goes next. Oh yeah, good routing. I don't know if it is good. No, here it's not. Oh, it's okay. Oh, it's okay. Here, here, this, here. I think this could still be optimized. For example, here we will have cross. Well, I have to go on one side for the input and down for the input and up for the output. Yeah, everything should go from here. Then it goes down, goes inside, and this down side, and then goes up outside. This is how we will do routing, and we can add all the diodes. I have to put the resistor here. The seal screen is a bit too large. Because we're in prototype, we can I have plenty of space. I can stretch it without any issue. It's still readable. Else it would compact the devices. But I'll stretch the device later on. I'll not show everything. For now, for today, it's just that I'm presenting this program. I will do the first placement. So this is just about the placement. Then we will talk about routing. So for today, let's finish the placement. SPI. This C erase. This one, where does it go? Goes to these pins. Yeah, goes around to. So let's put it around here. Yeah, see, goes to these. Fine, and we can. Should we rotate it? Right rotation. I will change the pins so the pins are mapped correctly. This pin goes here. Ideal if this goes here, this pin goes here, then this one here, then this one here. Because we have digital routing, we can put the pins anywhere. Let's do it now. So 25, 2, then 26 would be. It's Mozi for now, but it should chip select. Yeah. Up here. Which one should be chip select? 24 should be chip select. Or you get away. Then we have this one should be the next one. This is Mozi. So 23 should be. And probably 22 should be the clock. This is clock, right? Clock. Exactly. Up. This 3 imports. Base. Import the schematic, the netlist, and let's import the netlist. Now I select all the rat's nests. We see it lines up perfectly. Looks nice. Up with this. So here these are the voltage regulators. Yeah, they're fine here. We have to put the capacitors net from the voltage regulators. Yeah. So input should be left, then output should be right. Switches one. This is output ground. This is in. Okay. So the 5-volt input come from the fuse. Something like that. Here. Left, input on the left, output on the right. This one is more important, so we will put it on the right so route it better. This one can be routed on the outside up to here where we need it. Here, now we put the capacitors on the input and then the output. So the capacitors for the 8 volts, it's C8 and C14. 14 should go on the output right here. 8 should go on the inputs. This is ground, right? 8 should put it right here between this pin and this pin. And you want it as close as possible between the two pins. So mostly important, as close as possible to this pin. Second importance, as close as possible to the ground. It is less important because there will be thick traces to the ground everywhere, so the resistance will not be high on the trace and as coupling. But most importantly, this one. So we will have it somewhere this 5 volt exactly, like this. That's the input, that's the output. Very close. Still within the boundaries, but very close. We look at the assembly, not within the courtyard. Courtyard is also within drawing. This is not from the footprint. This is the sub-secret limit drawn from PCB R&D, from the GIA tool. Up this way we are next. And now we do the same for this one. So input C2, output C6. Output. Output. Like this. That's done. Ah, I didn't add. I should. On the schematic, I didn't add any bypass capacitor next to the component. I think I don't know if it is recommended in the design, but whenever I have an external component, I generally add as a bypass capacitor. Let's check on the memory. One is it? That's the USB connector. It's not. Now let me get it. Get the data sheet. I see. Should be flash. Does it recommend? I just want to be sure. Does it recommend? Almost. Again, bypass. There's an example application. All the characteristics. That's the package. Oh, doesn't say. Yeah. Oh, it doesn't really need any capacitor. That's weird. Bypass thing. Decoupling, nothing. Microfarad. Farad. Manufacturer. This is just manufacturer. Oh. This is, so it doesn't need an external bypass capacitor. I find this weird. I find it very weird. Let's have a look at other design files. I think this one doesn't have any SPI flash, but I know that the project. Hardware development data sheet. So this one, this Mini F4 development board. This has a connection to. This has a flash SPI. Yeah. Yes. Add one, and we should add one too. maybe it's not mandatory because it is not documented in the datasheet, which I find weird. Power. Have a look at the power input, power up rating, power down. These are just the programs. Maybe called VCC. VCC. Okay, that's power supply. Yes. It doesn't draw a lot. Power block. Tied directly to power supply. Okay, so I can also change that in my design. In my design, it is tied directly. So let's leave it this way. I have 0 ohm resistance, but we don't actually need them. I didn't know. I didn't check. Yes, warning. If no, it's just a warning. Okay, it's just a warning. But it means that they could be tied correctly and directly. I will not tie them directly because I don't know if I would want to use V and hold, because I think hold can be used for seconds IO if you want dual SPI or quad SPI. So you don't have to tie them, but you can. Okay, VCC. There's nothing in this data sheet about putting a capacitor to VCC. Let's here. Like the array protect. Okay. Hold. So VP cannot be reused. So we can really tie it to I. No, this can be reused for quad IO. I think we don't want to use it, but this is a prototype, so let's leave it open. Let's keep a 0 ohm resistor. For the next prototype, we won't probably need it. This is to pole. When brought low, we have to tie it up, right? Right protect is active low. Yeah. Well, hold is the same as reset, it's active low. And then this can be also used for quad SPI. So I don't know if I want to use quad SPI. I don't think that the PSOC has a quad SPI peripheral. It has just SPI, but they have a user diagram with quad SPI. It uses UDB blocks though. Don't know if I need. Let's try how fast it is. It is meant for human interaction, so it doesn't need to be really that fast. But we need to add, that's for sure, we need to add a decoupling capacitor for this one. C8. Options, attributes, input left. And normally, if I have to export the netlist again. So we don't need this anymore. This one, we should have a new component. See, up and yes, C22 component left here. So here, for example, the problem, I think this is VCC, this is wrong. Okay, that's the other way around. You cannot put next to each other, you have to decide. We will put it next to VCC, and then there will be the ground pin. Ground kit. Have decoupling capacitor next to VCC. And we need two resistors also. 27 and 20. There will be 7, 1, 3, and 7. This one here. It's not very block wide. I will use the 10 centimeters I have. How long is the board? 8.5 centimeters. 8.6 centimeters. Almost centimeters. And yeah, if it will be almost as long because I will have board going up here. Let's see. Now, components. What else do I need? I need the two pull-up the pull-down resistors for the USB. R1 and R2. Actually, we didn't. Where are the signals? This is ground. This is all here. Wait somewhere. One. Somewhere around here. The LED. Well, let's put the resistor next to the LED so we know it belongs to it's the R4. Up. The button. This R3. Let's put it next to it. Doesn't need to, but this way we know that the resistor is for this and this switch. And we are coming close. The crystal. I forgot about it. Where does it go? Come on. Oh. What are the pins? 42 and 43. Oh, yeah, 42. Next to USB, obviously. Here we don't need to have them close. That's not really important. But there should be some. It doesn't need to be. It doesn't. Don't want them to be too long because the signals are not too strong. You don't want to have to interfere with others, but we don't have any high-speed communication. USB is a bit above. And the clock needs 20 and 21. And again, the clock is completely optional. I think I will. What I will start is I will put it on, see if it works correctly, and I will try to. It gives some precise timing. I think it's important. Yeah, I think it does give some precise timing. 20 and 21, right? 1, 20, pin. I don't know. I've always seen it next to the oscillator. I don't know if it's better that it's next to the pin of the microcontroller. This I don't know. Let's have a look at this board. This board doesn't put it. Let's have a look at this board. Okay, this board puts it next to the clock. Doesn't make a focus. This is the clock, and you see the two capacitors are next to the clock. So I think this is the correct way to do it. I hope that, although this is a clone, it's not an original, but I think the one who did the layout also, and I've seen it most of the time this way. But I would have to read the manual. Okay, what else do we have? We have plenty of decoupling. Are all these decoupling? Not only. We have still a couple of resistors. What are they used for? R5 and they are for the voltage divider. Most of them, 2, 3 of them. We have 5, 6, 7. And there's a resistor which is missing. Yes, there is. The one which pulls. Yeah, the schematic is not complete. The one which pulls should be connected to the output here with a resistor, so it can actually pull. There's one resistor missing here and one K resistor. But for now, let's put the voltage pin 12. Pin 12 is somewhere around here. 19. So it's 6, 7, 5, 6, 7. 5, 6, 7. Then we have a voltage divider for. This is the voltage divider. We also have on pin 15, we have the resets, which you 8 and C19. Oh, that's not the same. Oh, 54 should be around here. 54. Seven. Then only locate near the pin around here. For the reset, we have R8 and C9. R8, that's the last resistor we have. It goes in here, and then this doesn't need to be next to the microcontroller. Let's not put it next to the microcontroller. Let's put it here next to this. This is reset, ground, 5-volt ground, reset. Let's put it next to, so it cleans the input of this R8 and C. Okay, now comes the fun part. I think these are all bypass. So many bypass capacitors. A lot of bypass capacitors. Where are all bypass capacitors? Yes, these are. So C1 VCCA. VCCA is on 63 somewhere. Really close to it. That goes here. C2 VCCD and then no, C3 VCCD and C4 VCCD. We have two of them. We don't put it on the same side because we have two VCCD. We have 39 and 6. Why 39? 30 is somewhere around here, right? 30. 39. That needs. Where's USB? This inline resistor should be here. This should belong here. That's the first one. 39. 86. And it doesn't matter which one goes where. Doesn't matter. We go here. Then we have C5 and C7. They go to the same pin, VDD8. Oh, I did something wrong. C5 is only 165. 5 somewhere. 5. C9 and C11 DDD. There are two of them. There's one which is here. Then D12 and we have two VDD, so there are 2 times. This is more important. 7, 7. So needs a bit more space on the side. 12 and C, they go on 2 cup. It's a lot, but then we have VDDIOs. That's 5 somewhere around here. That's in here. 16. Or it's 75. 75. Yeah. Then let's yeah. 18 and B. Yeah, it's on the corners always, but somewhere go a bit on the left. Okay, placement is done. This is how it will look like. So this is the rough placements. I don't need to stretch it too much, but I will still stretch it a bit so I have more space for the capacitor. So this, I will change the footprint for this. I will have more space for the capacitors here. Here the routing is quite good. Here it's a bit cramped. Here I think it's okay. But I still need to add 1 resistor on the schematic, and here it is a bit cramped, so I will put more space disconnect. Stretch a bit to the right. And once this is done, we will start with the routing. This is probably a bit of a boring part. I will still show you the routing a tiny bit for a couple of hours to show you how I do my routing. But for now, the rough placement is done, I will do the precise placements off screen, off stream, and off screen. No, on screen I will be on my screen, but off stream you don't have to watch it. And you will see the result. And still, once we start doing the routing, we will redo some placements, some fine adjustments, even finer than the one I will do next. But I won't do any routing off. So the next stream will be about routing once everything is roughly placed. And then I will not show you the precise routing. But once this is done, I'll probably show you the ordering. Probably show you the ordering. I don't know. Yeah, I'll show you the ordering once the parts are ordered. We need for. But for that, for today, the stream is done. And yeah, see you next time. Enjoy.